Okay, so this week's lab was talking about constant velocity motion, and we used this lab to create a computational model and an observational model of an object in constant velocity motion. So essentially the purpose of creating these two models was to create and compare observational data that tells us an object's motion and also helps us predict the object's future motion. And this is a big application of Newton's second law because we can use force, mass, and acceleration to help us predict an object's motion and to also tell us how it's already moving. So we use this law down here where final velocity equals initial velocity plus net force divided by mass times delta t, which represents the change in time. And so in this lab, since we're looking at constant velocity motion, we want to see that when our net force is zero, which it is, that the final velocity equals the initial velocity. So a bit of the procedure really quickly is that you wanted to move the object at a constant speed without it changing direction. So I chose to roll a toy car across a flat surface. And so this is the video that I put in. And so this is the video that I put into Tracker and plotted to create the graph. So we'll see here that plotted position and time on the X and Y axes. And so from our procedural video, that's what we'll call it, we got the initial conditions that when t equals 0, the net force is 0 all the way through. The initial position starts at the origin, and the initial velocity is 0.52 meters per second. So from the position and time graph, both are observed represented in blue and our computational represented in red, we see that it shows a positive relationship and that the object is moving in the positive x direction. Now, some similarities are that both models have the same final position, which is good. And they both demonstrate motion in the positive x direction and a constant velocity motion. And one of the main differences is just that the computation model slightly underestimates the position during the time interval. But that could just be because I used a different code than the starter code that was provided for us to this lab because I was having some difficulties with it. But it essentially gave us very similar and almost equivalent results. So when I say the starter code wasn't working for me, I couldn't really get the graph to represent the velocity of the object that I had rolled. So I just started over with a new one and then went through and defined the labels of xt, v, a, and dt, which represent position, time, velocity, acceleration, and the time step, and then wrote this while loop while t is less than 0.5 because this is the time that ends by the time the object, the toy car, reaches its final position. And then I just wrote down these velocity update formula, position update formula, and the time step, and then I plotted it on the graph, and that is how we get the data that is used here for our computational model. And so the important part about this lab is calculating constant velocity motion, because sure, we can observe it on a graph, but we need the numbers to prove us right. So to calculate the object's velocity, we use the velocity update formula, which is very, very similar to Newton's second law, no surprise there, and uses the velocity update formula to see that the object's final velocity is equal to its initial velocity, 0.52 meters per second. Therefore, we know that it moves with a constant velocity, especially since the net force is set to 0. And we know that the forces acting on the object are constant, equal, and opposite. And so this gets into the what if and what does it mean parts of the lab. So this means when it says what if the x-axis is flipped, so instead of the car moving in the positive x direction, it's moving in the negative x direction. Well, the signs of our position vectors will definitely change. But overall, on the position versus time graph, it would still show the same positive relationship. And then when we talk about net force, are we able to determine how many forces added together to give us a zero net force in the case you observe? And sure, we can identify a few forces, gravity and the force pushing the car forward, which is me in this case. And we know that gravity is a known constant, but we can also quantify the force using Newton's second law. And then if we find that the magnitude of these two forces are not equal, then there are most likely other forces acting on the system, like friction force, that are not accounted for, and that allow us to get up to zero in our net force, so that all the forces are equal and opposite. But overall, in conclusion of the lab, we learned that an object achieves constant velocity motion when net force is zero. The type of relationships between position and time, and how Newton's second law can be applied